Thank you so much, sir, and welcome to our Pranobonto's workshop. So let's start from us, Pranobonto, right? So Pranobonto is not just an initiative, it's a revolution and confession of us. Can we imagine a Bangladesh, my country, where health is not a privilege but a right? We know how expensive healthcare is currently in Bangladesh, where a child scraped knees in a slum doesn't go untreated, where the word first aid isn't just a foreign concept to our underprivileged people. That's the Bangladesh Parliament is building. So we take an initiative where we don't wear caps, but we wear first aid kits. We are not doctors, but we bring life-saving hopes to the streets. We don't wait for the change. We Pranobonto are the change. From slum area to forgotten village, Pranobonto works in with bandages, antiseptic, and above all, it's all about our empathy. So, Pranobonto is a youth lead passion power born not in a boardroom but in the heart of those who refuse to look away. But sometimes it's not a hospital that saves a life. It's a 16 years old with a heart full of courage and a bag full of basic. That's Panamonto, a youth lead initiative providing basic first aid and health support to the underprivileged. With that, I would really like to welcome you all to our today's session. With that note, I now would like to pass the floor in few minutes to someone who shared this vision and believes in the power of action just as much as we do. So please give us a moment. Now let's welcoming our today's speaker, Mr. Peter Morgan. Peter Morgan, sir. He is literally a disguised independent researcher with a lifelong passion for the foundation of physics. His work didn't just found in research. After earning a mathematics degree from the University of Oxford in 1978, if I'm right according to my research, he worked as a computer programmer before completing his MSc in partial physics at the Durham University, where we failed twice even before graduation. Joke aside, he chose a non-traditional academic path. Peter has been actively engaged in the theoretical and philosophical physics for over 30 years, where it's even hard for me to even pronounce the designations. As a lab associate at the Yale University Department in 2024, he has reminded us to closely connect through
Oh, oh dear. She has been cut off, I fear.
So let's start from the start. We were talking about his non-traditional academic path, where Peter has been actively engaged in a theoretical and philosophical physics over 30 years. That's a huge time, where it's even hard for me to pronounce this designation. So he has reminded closely to connect with these academic circles through seminars in London, Oxford, and his University Yale. With 11 peer-reviewed publication and growing recognition in the field of his quantum foundation, Peter Morgan brings deep insight in education and an inspiring perspective to the modern physics. Thank you so much, sir. Now, Pranamonto will be proud to welcome Peter Morgan to the floor. Thank you so much, Mr. Peter. The floor is all yours now.
So thank you for a very pleasant introduction. And I have to say, I feel embarrassed to talk about quantum physics when you have so many difficulties in Bangladesh. Not that we don't have difficulties in any other country, but still. And I wish you the best of luck with your healthcare initiatives. So much more important in many ways, but not something I can do at all. So I'm just going to talk about quantum physics. And so I'll try to give you some idea of how I came to these ideas. I've written some notes, whatever, so I'm going to look down a little bit. So it's been 50 years since I went to Oxford. I was 18 then, and I did a few years of just mathematics, and then in my third year, I started doing physics. I did quantum theory and a general relativity courses. Um, but I'm embarrassed to say I got a first class degree, but no one ever suggested to me that I should do research because I think I was not good enough. When it really comes to it, to do research, you have to be really very, very good, or you have to be very, very determined. And I wasn't. So I went and became a computer programmer for a dozen years. Then I dropped out of that really quite hard. Not something I recommend to anybody, but if it happens to you, then you can survive it. Here I am. So, and I'm sure you've seen many difficult examples in your own families and friends of people who survived things which you'd rather not anyone had to do, get through, but still they have survived. And really, what I've survived is not something I should brag about at all, to be honest, compared to what many people have to face. Um, so then 35 years ago, I started reading popular science books about quantum mechanics, got very cross at how stupid they all were, and I was hopeless. So I went and did a particle physics degree at master's at the University of Durham, and that really gave me a basis of how to do research because I had a really helpful supervisor, really crazy guy in many ways, but very helpful, and taught me not to get too absorbed in a particular idea. Even so, I was much too obsessed with particular ideas for about 5 years after that. But I was saved by marrying a person who I met at the University of Durham, who turned out to be a very, very good academic. So she had a job, she got a job at the University College London, then she got a job at Oxford, and then she got a job at Yale. This is not a common sort of person. This is a very, very good academic. And I learnt a lot from her. She's very, very good with people in a way that I'm frankly not. But still, you absorb a lot about the nature of academia, where people are very worried about their own careers. And so they really become obsessed with their own ideas and they don't have time for your ideas. And you getting past that is something that takes a long, long time. Really, I was 10 years and pretty much 2000 or so before I was starting to be wide-ranging enough in physics to actually make a contribution. Um, Now, I hope that all of you on this call are much smarter than me, and it will take you only a year or something to become really good researchers and so on. I fear that for many people that's not the case. I know many graduate students really struggle with the transition from learning to research, where you're expected not to go by the book, but if you go too far off the book, you're going to get problems. So only about 7 or 8, 10, maybe 10 years ago, I started to think in a slightly different way about quantum mechanics. Um, and ideas about classical mechanics started to come in ways that I got some encouragement from someone here at Yale back in 2017 who said, well, that doesn't sound like nonsense. 2 years later, I published an article that introduced these ideas in an appendix. It was actually about quantum field theory, but there was an appendix. Then, a year later, I was able to write that idea up as an article in Annals of Physics, so a good physics journal, but still it doesn't make an impression, you know? It's very strange. If the stranger your ideas are, the more difficult it is for people to take them really seriously, and more important, to be able to use them. You find that people say, oh, that's interesting, but they actually can't see how to use it. And it's only when they can write their own papers so that it makes a contribution to their careers that they will really start to be part of a whole program, should we say. There's a few little signs, even now, now 5 years later, there's just a few signs that a few people might perhaps be starting to write things in the same sort of idea. But it takes a long time when ideas are so different. There's a network of ideas here, and they have to be both complicated and simple. Because if they weren't complicated, someone smarter than me would have thought of this a long time ago. But if they're not simple, then they won't help us understand what we've done, what we have. So quantum mechanics is a perfectly good system. No one's going to replace it with something that's complicated. So you have to have something that's both complicated enough that no one's thought of it, and something that's simple enough that people want to use it once it arrives. And I'm not sure I have that. I'm kind of a crazy guy in a back room, and you haven't heard of me apart from this little chat because I haven't yet persuaded many people that there's really something there. Some I've given 18 talks in the last 5 years to various different places who've said, oh, that's interesting, but it's a slow business, a very slow business. You don't see that slowness when you read the histories, except, for example, you think 1925, people started, well, 1923, you started getting ideas about quantum mechanics. 1925, 2 years later, people, Heisenberg says, oh, 1926, a whole year later, Schrödinger says, oh, 3 or 4 years later, you have a textbook from Dirac in 1930 saying, this is what we're doing now. And you have Max Born didn't introduce the ideas about probability until 1927, I think it is. It's years pass at the beginning of any idea. And there are many ideas that come to nothing. Everything I'm going to say to you today could just become nothing by the roadside. And most people's ideas do. You have something like string theory where people have devoted their whole lives, and thousands of people have done, and maybe that's going to become nothing at all, except it won't, because there are good aspects to it, to the mathematics in particular, that really won't kill it. But still, you have to be willing, if you're doing research, for your research to become as nothing in the future. You have to be prepared to go to your deathbed saying, I worked hard and that must be enough. So if I've done anything interesting, it's because I've used what has been done by much smarter people. And in the last 50 years, there's an awful lot of literature which is very different in feeling, to my mind, to what you'll find in the earlier literature about quantum mechanics. So I started with only signal analysis because that uses Fourier transforms in Hilbert spaces in ways that are rather similar to quantum mechanics. You can find YouTube videos showing you how it's similar and different, but they don't really emphasize the differences. And there are subtle differences that matter a lot, and that's why you don't see quantum mechanics taught in terms of signal analysis very much. A little, but not very much. But then a few years ago, someone reminded me that data analysis is not the same as signal analysis. I thought to myself, well, machine learning is all about data. Physics is doing a lot of that. Maybe we need to unify machine learning with quantum mechanics. Frankly, that's so vague that it's hopeless. It's something that's in the back of my mind that perhaps in 10 years' time might become something, or someone else will say, well, that's kind of an interesting idea after all. But then there's a different strand of thought. There was always this feeling that we talk about particles as if they're obvious. And yet, with these data sets that we get from our experiments, how obvious is it that there are particles? You see tracks in particle detectors, but then for the more modern experiments, we don't see tracks. We just see an event happens, events, and those are recorded. So they are mostly obvious, but particles are at the heart of some of quantum mechanics problems. Position is okay, momentum is okay, but we can't have both. So there's some kind of weirdness there, even at that sort of very elementary level. And of course, there's much more complicated aspects like Bell's theorem and Cushing-Becker and Gleason's theorem and so on. So suppose we do say, however, that we only have data. In a way, that's even more obvious because our experiments create gigabytes of it. How do we get from data to particles and their properties? And in fact, I don't know. And that's why we have to pay attention to our quantum mechanics textbooks. We're not going to get new textbooks that start from the data and develop everything that is completely different from our quantum mechanics textbooks. It might be a chapter in the back of a textbook in 5 years' time. Someone at some point, if this becomes anything ever, will write a textbook saying we can start from the data like this and get to what we had in the past. So nobody should be thinking, oh, I'm going to give up on quantum mechanics. Quantum mechanics, what I'm saying is quantum mechanics is right. It actually does do everything that people have been saying, and that's because it's just mathematics. People often say that quantum mechanics is incomplete, so we have to make it more like classical mechanics. Now, many physicists won't say that, but there are plenty of those who do, and there are many philosophers who do say that too. Here, the message is the opposite, though. Classical mechanics is incomplete, and that's because of the no-go theorems like the Cushing-Becker and Gleason's theorem. So perhaps we need to do something to classical mechanics to make it more complete. That is something that to me by now has become so obvious that I can't see why anyone would doubt it, to be honest. It really is the opposite, however, of what people have been saying for the last 100 years. Quantum mechanics is more than just ordinary probability, though. It's an example in the mathematics literature now. It's very clear, I think, that it's what we call a generalized probability theory. It does more than you get from ordinary probability theory. And this is actually something that is already anticipated by a book by George Boole in 1854. 1854. He says in the book called The Laws of Thought that there are some situations where you can't bring lots of joint lots of probability distributions together as a single joint probability distribution. Those are what we would now call incompatible. And he always talks about relative frequencies, by the way, because in 1854, probability theory didn't exist the way that Kolmogorov created it in the 1920s. So there's a real long history to these questions about probability theory, mathematics. So the thing with classical mechanics is that we can make it be a generalized probability theory as well. We use the Poisson bracket in a particular kind of way, and that, however, is a way that's different from the way that quantization works. Quantization, I find it hard to say what the difference is. The Poisson bracket in the relationship as I see it is different from the relationship you see in quantum mechanics for the commutator. Even though that's the history goes back to Dirac saying, look, the commutator is the same as a Poisson bracket. Nonetheless, there's a serious difference there. There are theorems that say you can't have that as an isomorphism between those things. And yet there are ways of creating something, well, what I call CM plus. If you've seen any of the video, then you've seen that I talk about CM plus a lot. CM plus allows you to construct something that is isomorphic to quantum mechanics. It's not the same as the quantization path. So it gives you a different way of thinking about the relationship between them. So the last thing I want to say is that anyway, aren't we supposed to be talking about quantum field theory anyway? Quantum field theory is supposed to be our best theory. And for quantum field theory, if you look in the philosophy of physics literature in particular, but also physicists have been worrying about this, whether there are particles or not has become rather a tricky question. Since about 30 years ago, perhaps longer, some authors were concerned about this from long time ago. And in fact, you can now find some popular physics books. In particular, there's one by Sean Carroll and another by Matt Strassler that really try to bring quantum field theory down to a more elementary level. Now, I have a lot of problems with both those books, but I really applaud the attempt, should we say. So I'm going to shut up now. What I thought I'd do is I'm going to share. Someone has their microphone off. No, or perhaps since I'm opening up the floor, if anyone would like to ask questions. But I thought I would share my the talk, and if anyone wants to say, can we go to such and such a slide, then we can do that.
Peter, I have a quick question.
Yes,
Just
Sam.
before you get started, well, I put a little bit of a chat point.
So you did.
The point I want to make is that in theoretical physics, back in the early part of the 20th century, it was possible to do work by yourself, as Einstein did as a solo person. In theoretical physics in particular, would you say it still applies today, or do you think it's hopeless? Could you comment on that?
Well, if it's completely hopeless, then I don't know what I'm doing. But it's I think it is difficult. I think you do find very good people dropping out of physics and then trying to keep up their interest. And quite a number of them become journalists in the physics journalists and so on. Some of them do very, very good jobs of that. Others are not very good writers. So, you have to be able to write well as be a good physicist and someone who people want to talk to as well. It's another difficulty for some physicists, after all, that it's not if it's not pleasant to talk to someone, then they're not going to be a very good journalist, I guess. So I'm going to share this, and hopefully that will be okay.
Yeah,
So
slides came through. Looks very good. Thank you.
right, and on the other hand, hopefully you can minimize that and me and maximize the rest of the people. That's what I'm doing right now. I have now on one side the slides and me, and on the other all of you. So I'm assuming that enough of you had a look at the talk so that someone might have some questions ready, and just if you have, then just ask them. Otherwise, I'll flip through the slides until someone says, "Oh, I have a question about that slide." And I can also answer questions about slides in the appendices, if any of you looked at those, because I think having a little bit of a conversation about one of those might broaden out and gives you some context for what I've been trying to say in the talks. Yeah. So now I'm going to shut up because otherwise I'm going to keep.
Yes, I have a question.
Okay.
So I have read through your slides. So I have raised a question in my mind that the way you say it, the way you express average using the trace of operators look very much like quantum mechanical notion. So it is the similarity international or it is more general than the quantum mechanics?
So I think you mean this slide. Is this the slide you mean?
Yeah, this one. Yeah,
Right.
this one.
It really, this is such elementary mathematics that, even a high school student should be fairly familiar with some of the of what's going on there. So the trace of the product of two matrices just is this pair of numbers, this sum of numbers like this. Yeah.
Yes.
But that's just, oh, excuse me. I'm just adjusting something. So that's something that is just mathematics. It also looks a little bit like quantum mechanics, but it's something that can be used by classical mechanics perfectly well. Because it's just, and really, this is something that is being done in machine learning sort of software in any case. They're taking information, they're putting them into matrices and into things more complicated than matrices, tensors and so on. So in that sense, machine learning, I think, is actually more general than quantum mechanics because they don't confine themselves to using only Hilbert spaces, to only using matrices. They're using more complicated linear algebra as well. So there's that kind of aspect is in the business as well. But this really, if you think of this structure as what really is out there, then I think that's hopeless. The way I think of this is in an engineering way. If you've got many experiments, you want to use all that experience to let you predict what will happen when you have a new experiment. When you have a new experiment, what you usually do is you have lots of different initial conditions and you say, well, my new initial condition looks different, and so I'll use this same differential equation. But that is just a different way of doing things than approximating it by saying, I've got this experiment. Let me take you to this page in the appendix. So we have that relative frequencies give us a model of the Kolmogorov axioms over the rationals, because those are always ratios of integers, so they're always rationals. Probabilities give us a model of the Kolmogorov axioms over the real numbers. We can use algebraic models that give us real numbers as well, but they're more complicated kinds of models of the Kolmogorov. What you do is you take lots of relative frequencies from lots of different experiments, and you decide how you're going to interpolate between all of those numbers for some new experiment. But this is different from setting up your initial conditions, as you would for classical mechanics, where you use the fact you know what the differential equation is for all those different initial conditions you've already got. So it's a strange kind of way from a classical mechanics kind of perspective. But on the other hand, if you look at the modern classical mechanics, you find that actually this is the sort of structure that is actually being used as you find if you do if you look at the Koopman classical mechanics literature. There's this really wonderful. Oh no, hang on a second. I know where I want to go. I want to go to here. There is a really wonderful open access article by Steve Brunton and collaborators of his that's on this page in the appendix. This Koopman methods, that's 100 and something pages of how to use Hilbert space methods to work with chaotic systems. It's a wonderful, wonderful article that if you're interested in classical mechanics and in chaos at all, that's something you should really have a look at. So this is part of what's been happening in the last 20 or 30 years. Because Koopman in 1931 said, let's use Hilbert space methods for classical mechanics. But then it was used immediately by von Neumann and by let me see, right, and Birkhoff as well. To prove the ergodic theorem, but then it drops off the map. For 50 years, there's almost no papers about it at all. Essentially, von Neumann forgets it, and so everyone else does, I fear. But then Sudarshan in 1976 said, oh, we can use this for chaotic systems, because chaotic systems were becoming popular in some sort of way in the mathematics. And since then, there's been a gradual build-up in how people have been using these Hilbert space methods. Right. So here you see me talking a lot, and let's have someone ask another question. We'll see if I can answer it more quickly. So I've just talked a lot about this slide, and of course you have the talk as well that at NSU as well. But it feeds into what comes later in the talk. It's not directly connected. It's sort of illustrative of the fact that this can be perfectly good classical mechanics, classical mathematics. It's not something brand new. It's something, as I say, Boole in 1854 already had the beginnings of this kind of thing. But it's also keeping to relative frequencies a little, not talking about probabilities so much. Just say, we are interested in relative frequencies because that's what we get out of our experiments.
Hey, Peter, I just want to, can you hear me?
Yeah.
Yes, I just want to encourage our participants to ask questions because, hopefully, what you are talking about resonates with them. And if I were to start a question for you, Peter, would you be able to explain the double slit experiment so that people can even do it at home today? I mean, that experiment was done, 200 plus years ago? You and anyone can do that experiment. Anything you want to say about the double slit experiment here?
Right. So I have a slide about this because when I gave a talk in Oxford back in October last year, I had a 20-minute conversation with one of the people there, the guy who actually invited me to give the talk, in which we went around in circles where I failed to explain to him what I thought was happening in a two-slit experiment, which is obviously the simplest experiment. You should be able to say something about it. What I think is crucial is to recognize that when you do any experiment, you put some number of devices around a room or in a space that you want to know something about. You design those devices so they're interesting. You don't use a rock. You use something for which the signal level starts out low and then suddenly jumps. And when it suddenly jumps, you say, I'll record the time at which that event happened. And you say, and people often say, well, that event must be caused by a particle. But if you've just got one event, it seems to me a little too quick to say there is a particle caused that event, because the event would not have happened without that device being there. So it's at least caused by both the event and by the particle and the event, and the device. So now suppose you have this room in which you've got a number of devices, it's just a kind of display, then events will happen in them even when the lights are lights are off, when you don't put any power into your laser. And we just report the statistics of those events. But if we move other apparatus around inside the room, then of course the statistics will change. You've made a change, and so there'll be a change in the statistics. And so we want to describe those statistics. And it's always a question as to what you have to do to get a particular set of statistics is also interesting. Not only what statistics do I get if I have this particular situation. Now we know with the twin slit experiment, you get events happen in a pattern that looks very like a wave sort of structure if you look at many events. But when you look at single events, they're just kind of random. But that's kind of the point. They're random, but now you've engineered your system to give you precisely the pattern you want that looks like an interference pattern. And it happens that it's actually a very simple experiment, just two slits will give you that display that looks like an interference pattern. But you can also think of this as whenever you introduce something into this room that you're doing an experiment in, whenever you change something, that's going to change the noisy field, as I call it, or the noisy electromagnetic field, really, in a particular way. So everything is bouncing around everything in a really ridiculously complicated way that you actually don't want to think about. So that's what quantum mechanics is really good for. It's good for describing the experimental results of an experiment that is hopelessly complicated when you look at it in detail. The electromagnetic field, the noisy electromagnetic field, you don't want to do that. You might say, well, I'm going to wave my hands and say there's a noisy electromagnetic field, but what you're interested in is predicting what the results will be and engineering the results you want for the next experiment or for a particular piece of something that you want to sell, a new phone or new whatever it may be. There just don't have to be any particles causing the events. We engineer different modulations of the noisy field near each device. That's the story as I have it so far. I'm not clear how good that story is.
No, I was going to ask our participant friends, does that make sense? Or do you have any other question? Otherwise, I have one other question also, but let me pause and see participants. Do you guys have any question? Yep.
I have a question to
Sure.
Peter. Then from statistical metrics, the question is this framework closer to a reinterpretation of classical statistic, or does it aim to provide an alternative foundation for quantum theory?
The answer to that, I think, is actually in the pages about quantum non-demolition field theory. So what this does, this is after the place where I suggested people would stop, because the previous pages are quite complicated, but these ideas on this slide, I think, are accessible, hopefully. So what you get out of this is what I call a quantum non-demolition field theory. It's a commutative algebra within quantum field theory that, as far as I know, hasn't been really discussed as much as it should be. It is something inside quantum field theory, so it allows you to use any of the tools that you have available in quantum field theory. But signal analysis is something much simpler than that. Signal analysis is just the analysis of a single signal. It doesn't even have any probability theory in it. If you put in probability theory, then you obtain what's called the stochastic process. This is something where instead of a time-ordered, a time-indexed set of signal values, instead you have a time-indexed set of random variables. So it's immediately more complicated than just signal analysis. But that's not actually complicated enough, because quantum non-demolition field theory actually works in 1+3 dimensions, just the same as quantum field theory does. It also includes quantum noise as something different from thermal noise. So that's different as well from most stochastic physics, where you just talk about thermal noise. Thermal noise and quantum noise are different. And also it allows you to use generalized probability. So with all those things added to stochastic processes, you get quantum non-demolition field theory. So in that sense, this is absolutely old stuff. This is something that in 1930, this mathematics was already introduced for quantum field theory. In another sense, this is taking something that's only become much used in the literature, stochastic processes, about the classical quantum transition, should we say. For the last, 20, 30 years, it's become much more used than it was, say, in the 60s. I mean, not that people didn't know what stochastic processes were long before that, but they started being used much more intensively in the last 20 or 30 years, I think. So this is both giving you old mathematics and rejuvenating it and making it more comprehensible, I think. At least I find it more comprehensible. At the same time, because this doesn't talk about particle properties, this is so different that it took me 10 years to stop talking about particle properties all the time. Whenever you read an article, they begin with, we take the light and we take the photons, and they start talking about particles immediately. They have two photons in their apparatus that they are just using, whereas I'm saying, actually, there's this huge number of degrees of freedom in the system. When you consider it as an engineering problem, it's clear that there's a lot more data in this needed to really get into the details of what's happening inside a piece of apparatus like that of Gregor Wies's. So, yeah, well, I'll stop there. But I mean, should I clarify any of that?
Regarding your speech, I have a question, which
Okay.
is that the quantum physics is using in many ways, like the modern electronics, like smartphone computers, and the new thing that came up, the quantum computing, and also in using in medical images, and also understanding the whole universe at a deepest level. So how do you see the quantum physics future?
It's going to continue whatever I say, because it's just hardware engineering. You're trying to produce a better computer, something that solves a particular problem. And often, as you said, as in one or two of the examples you just said, that's going to be a medical problem because you want better medical imaging. And medical imaging is starting to use ideas from quantum mechanics, because you can use two photons, as the standard way of describing these things would be, to give you information that cannot be obtained quite so well from the standard ultrasound and people are using lasers to get information about quite deep within the skin by using the right frequencies and by using sophisticated analysis, really sophisticated mathematics, actually. But so, well, again, I have this slide about, I have this slide about quantum computing. I just think a computer does what it does. Once you've built it, once you've chosen what to build, you give it a particular set of input, you'll get a particular set of output from it. The tricky part is deciding what to build. To decide what to build, you have to understand what the hardware is doing in a much more sophisticated way. So it doesn't matter whether you describe the experiment, though, using quantum mechanics or using CM+ or some other system. What matters is what kinds of intuitions it gives you. What would be the next good way to construct a new computer, something that will be faster than the computer you've got already. And bear in mind that the existing computers we have are enormously sophisticated. You're talking about thousands of millions or trillions of individual silicon devices within a single computer now. And so whatever you build has to compete with that kind of level of attention to the details of hardware. But from a CM+ perspective, well, I just present this slide, I suppose. I mean, you have quantum noise as a resource now, as well as thermal noise. So you're trying to use that as a tool. And you will find the idea that quantum noise is a resource, a computing resource, in the literature quite a lot now. But this way of thinking about quantum noise as something like thermal noise, but different in a very specific mathematical way, Lorentz invariance, really opens up to different kinds of intuition as to what your apparatus is doing. You no longer have to say this is incomprehensible. You can say, I can have a classical model of this if I like, but I'm going to use quantum mechanics anyway because that's better mathematics, right? And that's what you see said about de Broglie-Bohm, after all. People say, this is all very nice, but it's a lot harder than just doing a three-dimensional Hilbert space, right? So you're always going to use the easier mathematics as an engineer, but you also want to have an intuition in the back of your head that says, this is what I'm really doing. This is what I'm engineering my system to do. And this kind of way of thinking about it, I feel, gives that kind of intuition a boost, hopefully.
Yeah. Along the same lines, Peter, I mean, as one of the questions was around today's computers, as we build transistors that are getting smaller and smaller, now we're talking about 2 to 5 nanometer feature size, right? At that scale, things become tricky because quantum effects have to be taken into account.
What I would say is quantum noise becomes an issue in a way that it isn't at smaller scales, but also thermal noise, of course. And indeed, for most classical computers at the sort of 2 nanometer scale, I think that thermal noise is more important than quantum noise. It's only when you reduce the temperature down to the sub-Kelvin level scale that quantum noise starts to dominate the behavior of these devices. And that's why many of these devices are cooled to such temperatures, because you don't want the thermal fluctuations causing affecting the physics of the quantum fluctuations. And the great thing about quantum fluctuations is they're very, very steady. Their amplitude is fixed by Planck's constant, which does not change anywhere. Whereas thermal noise, getting the temperature of your device to be 300.0000 Celsius, Kelvin, sorry, is very difficult. Getting six figures of accuracy for a temperature, but 6 figures for Planck's constant is trivial. That's just what it is.
But
it's still the amplitude of a noise. It's a really good standard candle, shall we say, for a particular kind of noise. And you can distinguish the thermal and quantum noise because they are different kinds of noise, different spectra.
Now, there are processes in nature, let's say photosynthesis, olfaction, or sense of smell, and even mutation in DNA. There are now conversations saying that these are quantum events. Now, these are not at millikelvin temperature.
No.
How does nature, execute these quantum phenomena?
Okay. So I'm going to, after this question, Sam, I'm going to cut you off. I'm going to insist that we have to have a student ask a question. But I think that it's an interesting question for all that. I mean, who knew that Sam would ask interesting questions? What I think is happening there is that evolution has been working with quantum noise and thermal noise and lots of other kinds of noises for many, many millions of years. And insofar as it's useful, it has happened to be useful to use quantum noise instead of thermal noise, instead of other kinds of noise, instead of other kinds of influence from outside, then I suppose some of those things we do may actually depend on quantum noise being an absolute nice constant in the background. But I have no confidence. I just don't know that literature very well. And also I'd be reading it through such a different lens than most people that it's very hard to read that kind of stuff because I have this different perspective. I'm always trying to translate the articles written in terms of these standard ways of talking about such things into my kind of way of thinking, and that slows me down a lot. Not something I recommend again. It's something to bear in mind that it actually makes it more difficult if you are talking a different language from other people. So let me invite other questions.
Yes, I have a question. I read the PDF that you given yesterday. So I'm just writing everything here.
Right?
And so the question that is very big question. So your framework treats multiple probability spaces, single operator based structure, and avoid explicit use of Planck's constant quantum sorry, sorry, the question is another way. So my question is that you wrote that multiple probability spaces are contained in a single formal structure, right? So
Yes.
can you give a simple example or institution behind this idea?
Now, this slide is what I think you're talking about again. Yes? So in some ways, this is just a simple starting point for what comes later. It says this can be used classically. If you have lots of data and you want to analyze it, then you can do anything with it. You can apply any transformations at all to it. But the question is what's useful? Because given one set of data, if you can apply any transformation, you can make the result look like anything at all. Because there's so much flexibility in having any transformation. So you need to limit yourself. And the way that quantum mechanics limits you is to talk about particle properties. And it works most of the time, and indeed, perhaps all the time. It gets a little trickier when we get to quantum field theory, because there we say, in order to describe this whole experiment, we need to use an infinite dimensional Hilbert space, and indeed an infinite number of degrees of freedom. I'm not answering your question. What should I say? So I guess the thing, see, for example, this following slide, everything for quantum mechanics and for classical mechanics is exactly the same, except that what we say is that if it's non-commutative algebra, then it's a quantum algebra. And we've always said that if it's commutative, then it's classical. You'll find that in the literature everywhere. There are other finer distinctions made by people, but nonetheless, this is the basic single thing that's said. And it's because when you look at classical mechanics, there's just addition and multiplication. And those just give you a commutative algebra. But it's not said that there's the Poisson bracket as well, which makes this not a same simple algebra the way that you have in quantum mechanics. Quantum mechanics just has addition and composition because it's all transformation algebras. Quantum classical mechanics you can make be the same. Now, once you've added in that non-commutativity, you've got something that looks very like quantum mechanics already. Now you start saying, well, this I could use if I wanted to. On the other hand, there are no textbooks that tell me how to do it for particular cases. So you don't want to do it because you've got all these textbooks that show you exactly what to do for any given experiment. So you're not going to want to do this. But this can be in the back of your mind. This is like thinking to yourself, de Broglie-Bohm is hopeless, but on the other hand, sometimes it's useful. This is something very much like that to me. I really don't want to sell this as anything like a theory of everything, for example. This is just a way of thinking about quantum mechanics and classical mechanics and the relationship between them that gives us a background, a different kind of background than we've been used to. It takes some getting used to. And again, it's taken me 7 or 8 years to get to this point where hopefully I can make some sense. Yes. There's been thousands of people have been working for 100 years on quantum mechanics to make it make sense. And it's going to take not necessarily as much effort as that to make this make sense in the way that quantum mechanics textbooks make sense, but it's not something that's going to happen overnight. It's something to have in the back of your head, something that is good to have at the beginning, earlier rather than later. So, learning this in 5 years' time when everyone else is already thinking about it is not as good as learning about it now, always assuming that this makes any sense at all in 5 years' time. It may be gone, forgotten. And you really have to, when you're doing physics research, that has to be in the back of your mind. This may not exist in five years' time even, but you do it anyway for the curiosity of it, for the fun of it, I suppose. But go on, hit me with something. I'm actually happy to carry on. As you see, I'm quite capable of talking too much. But as long as you're willing to ask another question, I will keep going.
Yes, I would like to raise a question.
Okay.
Thank you so much for giving me the floor. So my question is that quantum physics is quite a complex subject. I mean, a really complex subject. And today's people really want everything to be very easy, like in the palm of their head. So how do you see AI in the field of quantum physics?
Right. Well, as I've said, machine learning plays a part in the sense that it also takes data and tries to make sense of it. Quantum mechanics takes data, tries to make sense of it. So in a way, they're in the same business. And I think machine learning and large language models and all the rest can inform what quantum mechanics will look like in 5 or 10 years' time. I don't, I mean, there's so many discussions about what AI is going to look like in, next week, still less in 5 years' time. And I feel sure that some of the mathematical methods, which are really complicated, under the hood, there's really complicated mathematics going on. Whenever you ask an AI what the color of such and such a dog is, then it will tell you what the color is, but there's a lot going on behind the scenes. There's a lot of very complicated mathematics underlying it that, in some cases was only discovered less than 10 years ago. So that kind of mathematics, I think, will have an impact on quantum mechanics once it's registered that machine learning and quantum mechanics are doing the same job. They're analyzing data. Machine learning has discovered a lot by focusing on neural networks and so on, and how that's similar but different. So you find there are similarities of sorts between what machine learning does under the hood. And I suspect that quantum mechanics can have a similar sort of relationship with machine learning, a way of organizing things. One thing that machine learning does is some of them really pay attention to probability theory. Others don't. The ones that pay attention to probability theory, my sense, really is a complete amateur about this, is that those are easier to understand what they're doing inside them. What generalized probability theory does is it introduces a way to be more complicated without being totally complicated. It allows you to organize what's happening inside a machine learning, perhaps. But now I'm thinking to myself, if we're going to post this to the internet, people are going to be really horrified at how naive I am about machine learning. They should be. So I won't say any more, I guess. But you can ask something else and see whether I say something even more stupid.
Yes, Peter, I have a comment maybe, and also a question for you. The comment is, you mentioned already Poisson bracket and generalized probability. For me, the role of AI is instead of asking you, or in addition to asking you, I can just ask my chatbot, right? And it'll give me the 6-year-old version, a college student level version, and the like.
Yes.
Which adds to my intuition, as you're also emphasizing, for us to make something to make sense, it has to sort of be consistent with something that is intuitive to us. And that's where I see the benefit of AI. And the machine learning part also, I would say, is coming. There is a field called quantum machine learning. Whether it's hyped up or not, we'll have to see. But my question to you is, do you see, the role of AI being such that it enhances our intuition? Because we can now ask just just by prompting, tell me, explain to me in many, many different ways. A human may give up on me because, it's too detailed or become impatient. But AI, never does. It will politely tell you in any different directions or any level that you want.
Well, I think you get a better answer to that question out of your AI than you will out of me.
No, I was just getting your sense of, is that something that you also find useful, as you do your own research, perhaps?
When the two or three times I've asked AI, well, I've had this conversation with you, of course, it always tells me how good my ideas are, and I think to myself, no, that's not what I want. And I know that if I was more sophisticated about the way I asked it and said, be as aggressive as the most horrible questioner in a seminar about the ideas I've just presented, it will perhaps say something so critical that I'll realize it's all nonsense. Um, but I've not yet dared to do that. So
Yeah.
it
Mhm.
seems to me that there are those kinds of, you have to become really experienced with it, but you have to really not get tempted by it encouraging you to think that you're right. And I've seen too many people, friends and otherwise, say how AI agrees with them effectively. And I'd rather not have AI telling me that. I'd rather have someone telling me that that this particular page has this mistake on it or whatever. Um,
Yeah, that's right. Prompt engineering, as you know, is a thing.
is a crucial, yeah, people
Yeah.
are experts at it. Yes,
Yeah.
yes.
Now, for our friends joining on this call, how are you guys thinking about, the relevance of quantum in the health area? Do you see in diagnostics certain devices becoming now affordable? Have you heard anything along those lines in Bangladesh? Either startups, promoting an idea of, quantum physics-based sensors, for example. Have you heard anything along those lines?
Quite not much recently if we like analyze our Bangladesh situation, but people are really curious about that fact because if we look at our education system, it doesn't quite relevant to this topic. They don't promote it or like let us show it. We have to be in our own case to actually prove that fact that we need this subject. So people are more into the AI based things more than the thing that they have to be working in hand to on hand.
Yeah.
Very
So I
good.
guess
Yep.
it needs more publicity to actually make people understand how this is so important to the world to actually excavate. Thank you.
Yes. Yes.
Yes, I was very conscious before I came into this call that nothing I can say, I think, really informs the kinds of issues you have. I can hope that it might make a difference in 10 years' time, but I don't even know that that is true. Perhaps in 50 years' time, well, I won't see it in that case, but that's okay. I mean, everything is, I always think it's much more teamwork than it is anything else. You're handing off to other people to do it better than you. And that's no different for someone like, for a group like Pranobonto, which, is going to be um, handing off a lot of things to other people as well as starting their own new things as well. Teamwork. Well, that's an old story.
Yes, yes. Now, one other thing I want to mention again, it's a bit of a comment. I'm a chemical engineer by background, so familiar with things like at the molecular level, right? So there is an area you may have heard about called quantum dot. These are molecules that have, some kind of a quantum effect because they radiate light in a certain way, and so they're used in flat panel displays today. So actually, a Nobel Prize was given for the people who did the work 2 or 3 years ago. So this is an area where I can also point to, and also known as nanomaterials, sometimes quantum materials, they're essentially synonymous to me. So anything at the nanoscale, single nanometer scale materials, there's a lot of interest and research activity. So something that you may want to consider exploring and researching as you think about your careers going forward, college and high school level.
Yeah, I guess so. But before asking another question, I would really appreciate Mr. Peter Morgan because this subject really gained my curiosity. And sir, being so determined on this subject, really appreciate. So
And
I heard it
I
from
want to
somewhere
add
that
some.
I really want to know that what is quantum entanglement and why did Einstein call it spooky action at a distance? Can you please clarify it for me?
Um, Anything I'm going to say is going to be very different from what you'll read in the textbooks. I don't have a slide about entanglement. What I think is happening here is that generalized probability theory is about more than probability. There are other areas of philosophy where things are about more than probability as well. You have what's called causal modeling, which is Udaya Pearl's sort of. There's a very good book about that, where part of that story is about intervention as well as probability. If you know, if you can intervene to create different outcomes, that can give you an idea of what causes what. But when it's statistics and not, like if you're talking about a ball hitting you and bang, that is very definite. If a ball hits you, your head is going to move. But when you're talking about medicines or anything of that kind, when you give someone a medicine, they may or may not respond badly or well, or it may cure them, it may cause them to die, even in some cases, if they have a bad reaction to a particular aspect, it may be just the base, not just the chemical. So there's that kind of thing is going on. You've got both probability and intervention or contingency, as a philosopher would call it. So it's contingent. Whether you do one thing or another causes things to happen differently. That's the word contingency. Contextuality is a word that's used in about the quantum mechanics, and it's said that classical mechanics is not contextual. What I'm saying here is that classical mechanics can be contextual if you're an engineer. If you're a hardline, there's a real physics state, then it doesn't work for you. But as an engineer, it works pretty well. So when you come to entanglement, entanglement is something that happens only when you have two particles. And you're asking about what happens to one particle when you have a particular situation, a particular set of conditions. Now you change the experiment in different ways. Things are just more complicated than this. It's not just about probability, it's about what preparation you're putting into the system. So what entanglement does, it describes a particular state of affairs, a particular sets of preparations that are not easily described using classical mechanics. And actually, this does go back to, well, this is kind of about the Bell inequalities. Let me see. So what you have here is, I mean, this is a fascinating experiment from 1995, more or less, 30 years ago. What I like about this is how clear his schematic is, that he is just going to store the times at which events happen and which of these devices it happened in and what the modulator settings were. And out of that comes this data. This is just a data set, and it fits on a single CD. It's sort of 500, 600 megabytes. It's a completely classical data. There's nothing about entanglement in this. It's just something you could apply signal analysis to. But when you start thinking about what the colors are, what these different discrete values are, you get this number 2.714 that says this is an entangled state. You've engineered your whole apparatus so that this classical data looks weird when you look at it through this particular lens of this particular calculation. And that's a calculation you can do with CM plus that you can't do with classical mechanics, if you think of it as just two particles going along separately. So this is entirely classical information that's being looked at through a particular lens. This is not a story that many people who work on quantum information, well, perhaps they recognize it, perhaps they won't, but they'll recognize that this is what the data looks like. Yes, when you look at it through this particular calculations. And this is part of why I say classical mechanics is not complete. It's not computationally complete in this particular sense. So that's what entanglement is. Sort of.
Just, I have a question, and last question this is, and before going to the question, actually when I was listening Peter's lecture, I was silently wondering that why you haven't been nominated for the Nobel Prize yet, huh? Sam, do you think?
For one thing, I'm 68. So that makes it impossible because by the time this becomes well known, I'm going to be 104, assuming it's right, or I'm going to be dead. And you can't get a Nobel Prize if you're dead. But also, I kind of don't play well with other people. And one aspect of getting a Nobel Prize is that people say, oh yeah, I know who he is. And also when you look at my papers, they're kind of messy. They're not nicely written. So there's that as well. And the other thing is that if you do something simple enough that everyone says, oh, I could have done that too, you're not going to get a Nobel Prize for that. Yes? That's the ideal, really, is to say something that's so simple, or at least looks so simple in 10 years' time, that people don't even remember me. So, do you know, 20 years ago, I would have said, my ambition is to have a Nobel Prize. But I've kind of gone past that now. Oh, you need to turn on your...
What do you think, Sam?
What does Sam think?
Oh, what do I think? No, I agree with Peter that, his work is original.
Too original.
I've been encouraging him to, keep pushing on. So let's continue that. Before we let go, I think we're at the top of the hour.
Yes.
Any view on quantum information science? Because we see that as well from your vantage point.
I would just repeat what I'd already said, to be honest, Sam. I know too little about the details. I'm just too dangerous.
Okay. No, I just thought maybe this is an area, is it a new emerging area, or it's pretty much a continuity from what you're seeing?
I think it's continuous. This doesn't change anything in some ways, except it puts in the back of your head a little mind worm that works differently. This is not de Broglie-Bohm, and yet it looks a little bit like de Broglie-Bohm, because you get trajectories out of it, and it actually is like consistent history's interpretation of quantum mechanics as well. It's like Nelson's work, except that it's all about fields. So the field theory aspect of this, see, that's the other aspect of this, that most interpretations of quantum mechanics do not play well with quantum field theory, whereas this is absolutely down the line more about quantum field theory than it's about anything else. So from that respect, I feel very comfortable with, the feeling that maybe it will have a street sweeper outside. Hopefully it's not too distracting for you.
No, it's all good. Just wanted to give a shameless plug for another Yale friend of mine. His name is Luciano Floridi. He's another Oxford Don. He came to Yale 2-3 years ago. He's now the founding director of the Center for Digital Ethics here at Yale. He has written the book called A Brief History of Information, where there are 3 to 5 pages in that book. It's a very tiny book, by the way. It's about 100 pages long, but beautifully, beautifully written. Talks about, history of information, information theory. Very readable, I find. So if you guys are interested, I would recommend that book, A Brief History of, or a very short history of information. It's the series, apparently. Very, very well written. So another Yale, just so you know, if you're interested in the quantum information science area. That's all from me. I hope it was useful to you all. And thank you, Peter, for making the time. It's been fun. This is a Q&A. I like this format, by the way. It's a lot more engaging.
Well,
yeah.
Elliot, I have lots of questions about quantum, but time is very short, and I write lots of questions here from Peter's lecture. But I really love this lecture, and thank you very much to Peter. Plenty of love from Bangladesh, and please visit us.
you're gonna have to
So Peter, now you have more friends in Bangladesh than just
Well,
one, me.
I hope
and
I hope I
thank
haven't
you,
put them
and
all
thank
off.
you.
But thank you, and I
Yes,
suppose
and
I
thank you
will
very much.
say goodbye.
And thank you very much, Sam sir, for joining us. And we are very glad you, and also Peter. Please visit us, Bangladesh. You have to come.
Thank you very much for the invitation. I will take it as an invitation. Right. Okay. Well, I will say goodbye. I suppose I will stop.
Yes, thank you.
Yes,
Thank
Thank
you,
you,
everyone.
thank you
guys.
so much, sir.
Thank you,
Thank you,
sir.
Your
guys.
insights were truly eye-opening. We are grateful for the way you made such a complex topic feel so alive. It was an absolute honor having you with us today. Thank you once again, and goodbye with a deep appreciation. Please visit Bangladesh not as a researcher, but as someone who belongs to. Thank you so much, sir.
Thank you.